Okay. Okay, do we start over or what? Okay. Okay, we're going to cover memory controllers. As I said, some people didn't have audio apparently. I don't know why, but it happens. This is an example of starvation, as you can see, right? You starve someone, and that's not good. Any kind of starvation is not good. Human beings are very good at starving others in general, these days especially. So we should avoid that everywhere. We're going to look at the memory system design, but I think there are even more serious implications of starvation. Okay, so why do we share resources? Because we don't want to waste things, right? If you actually dedicate a single resource or a single slice of the memory system to a single core, then what you're doing is really replicating the resources, right? This is replication in the end. And there could be many resources that are shared: functional units, pipelines, caches, buses, memory, interconnects, and storage. If you dedicate all of that to a single core, and if you replicate them, it's very expensive in the end. So if you share resources, then you improve utilization and efficiency, and that leads to higher throughput in general, which means that when a resource is left idle in terms of capacity or bandwidth, some other thread that may need it can use it, right? And this way, you don't need to replicate the resources. Also, you don't need to replicate the shared data, right? If you actually share a physical resource, you don't need to replicate a data piece that's shared by multiple processors. Whereas if you replicated that resource, you also need to replicate the shared data, which is very expensive, as we will see when we talk about, for example, cache coherence, right? We're going to talk about cache coherence in lecture 24 or so. And there we'll see the effect of replicating shared data in terms of performance. Okay, the other benefit of resource sharing is reducing communication latency. If you have a single resource that is shared that you can access, then you can access it very quickly from that shared resource. For example, if you have a multi-threaded processor and two threads share data, they can access that data in the L1 cache that they may share, right? And that could be very fast. So if they had separate caches, then the data needs to move between the caches somehow. And as I've kind of alluded to, this resource sharing concept is really compatible with the shared memory model. Multiple threads share memory, and this is at a programming level. You really share the different memory locations. And at the programming level, you share them. If you don't share them at the physical level, then there's a mismatch between the programming level and the physical level, right? At the physical level, you still need to move data to satisfy the programming level sharing. We'll see the shared memory model when we talk about later multiprocessors. But essentially, a thread can do a load to a memory location. Another thread can do a store to the same memory location. And they really share the address space, virtual address space in general, but it could also be the physical address space. Okay, so clearly resource sharing has a lot of advantages in that sense. But of course, like everything, there are advantages and disadvantages. That's part of the function of this course. We have advantages and disadvantages, and we really need to study all of those for any idea. And any idea, you can study advantages and disadvantages. That's what we're going to do today also, especially with memory controllers. So one downside of resource sharing is it results in contention for resources. When a resource is not idle, another thread cannot use it. Basically, you delayed that thread. Whereas if you had replicated the resource, another thread could have used its own resource, right? But we know that that's expensive. This applies to bandwidth. This applies to space also. If the space is occupied by one thread, another thread needs to reoccupy it. Is everything good in the sound? Okay, people are still hearing me, good. Okay, so if you have this sort of contention, this sometimes reduces each thread's or some thread's performance. Clearly, the thread that is denied service for some time gets lower performance compared to when it's run alone on the same system. This is going to be our comparison point. If you have all the resources to yourselves, you have some performance. If you're sharing resources, you have some other performance, which means that when you're sharing resources, you will very likely slow down. Unless there's some constructive interference that happens between threads, but that's usually unlikely, unless threads are doing a lot of data sharing between themselves. Right? It's possible to have constructive interference. For example, a thread may open a row buffer that another thread is going to use. So that row buffer may open earlier than it would compared to when the thread is run alone. That is constructive interference. Not all interference is destructive in the end, so it's good to think about it. But most interference in general is actually destructive, meaning it hurts performance, at least in real systems. Okay, so basically thread performance can be worse than when it's run alone. And we have seen that last time. We're going to see it more and more. Another issue that's related is performance isolation. Basically, once you're sharing resources, your performance isolation goes away if you don't do some things carefully, of course, as we will see later on. Meaning you get some performance when you're running with some threads, and then you get some other performance when you're running with some other threads. So your performance really varies depending on what other threads you're running with together with, because the interference patterns depends on what the other threads are doing. Right? Meaning this actually has a lot of implications. I already said this actually, co-executing threads. If you're a programmer, for example, you optimize your performance, you get very good locality somehow. This is assuming that you have access to some resources. If those resources are denied to you because some other thread actually interferes with you, then your optimizations as a programmer may be useless, right? You may not get the performance that you actually optimize for. This is the importance of providing some sort of predictable performance or predictable resources to a thread. That way, programmer can optimize for those resources, right? Whereas if the programmer doesn't know what kind of resources you're going to get, it's going to be very difficult to optimize for an arbitrary amount of resources. It's possible to do, but you need some other mechanisms for that, and we may see some of that later on. Okay, so in the end, if you have uncontrolled sharing, this degrades quality of service that different applications or threads experience. I call uncontrolled sharing free for all, because basically there is some mechanism clearly that decides who gets the resources, what is the scheduling policy, for example, in the memory controller, what is the cache allocation policy. But in the end, this is not aware of threads. It's really free for all. For example, if you do LRU, least recently used replacement, and insertion in a cache, that doesn't consider which threads are actually doing the replacement. It's really, in a sense, free for all. Whoever gets the least recently used or most recently used block, they will get the priority in the end. And whoever has the least recently used blocks, they will get deprioritized. Okay, so this causes unfairness and starvation in the end. So basically, if you're sharing resources, which is really important to do today, you need to efficiently and fairly utilize the shared resources. You have memory controllers, for example. As we discussed last time, memory pins are quite expensive. You don't want to replicate them, and you want to share them. So you need to actually really fairly figure out how to share these resources. Let me give you an example with caches. This is actually from a paper from 2004 that looks at how to do fair cache sharing and partitioning in multiprocessor architecture. There are more papers on this topic that we may cover if we get to it. But this happens in any resources in the end. So if you look over here, there's a blue thread. If it's running alone, it's using its L1 cache and it's a portion of the L2 cache. And then there's an orange thread. If it's running alone, it's using some amount of L1 cache and L2 cache. But when these threads run together, somehow L2 cache resources are mostly allocated to thread 1, the blue thread, and the orange thread doesn't get enough resource in the L2 cache. This could be because blue thread may be very intensive, for example, right? It brings a lot of cache blocks into the cache, whereas orange thread doesn't access memory at the same rate. But on the other hand, orange thread may have very good locality in the use of those cache blocks. So it may actually lose a lot of performance. And this paper deals with such issues, how to actually fairly share caches, which I'm not going to talk about. There are a lot of strategies over here. How do you partition the caches while also enabling sharing? How do you do dynamic partitioning of the caches such that each thread gets good performance or the best performance that it could compared to when it's run alone, etc. Okay, I think I've kind of motivated this, but as I said, unpredictable performance or quality of service, lack of quality of service is bad because it makes programmers' life difficult. Programmer may optimize their program, and then eventually they get bad performance because they don't get access to resources like caches, for example. And the performance varies very much depending on co-runners. It also can cause discomfort to user, right? In the end, some of the programs are actually very much dependent on the service quality that the user gets. For example, you're running a video, and that video may degrade in terms of quality if some other program is hogging the memory bandwidth that the video is trying to bring into the caches. So an important program can starve, basically. Hopefully these are interesting. This happens in software also. So don't think that resource sharing is only in hardware. There's also a resource sharing in software. For example, in operating systems, you partition the storage devices. You partition the memory. And the amount of, you partition the processors actually, the amount of time you give for a software thread on some cores affects the quality of service and the performance that thread gets. Right? If you give less time, then the performance of that thread may reduce. In fact, I had done a lot of work on software resource sharing when I was at Microsoft. One of the issues at the time was storage was shared across different applications. So when you ran, I hope this is fixed right now, I'm not sure. But basically, when you run Excel, PowerPoint, Word, these all used to have a common software base to access storage. And that common software base may lead to some denial of service issues. For example, when you're saving a huge Excel file, at the time, it used to take a lock on a portion of the software. And if you were about to do something on Word, you couldn't do it because Word needed to bring something from software storage, and Excel was all holding lock. So you can see that now there's resource sharing at the software level. And this was kind of unintended. In my opinion, this was really a bug. But again, the reason that the resource sharing existed across different applications was people wanted to optimize for a better software structure or easier to maintain software structure so that all of these applications would go through the same storage subsystem in software. You could argue that this is a good choice or bad choice. Clearly, the resource management was not done well, such that one application who was hogging the software resource was denying service to another application because of this resource sharing that was caused. So this happens in software also. It's not just hardware. In fact, this happens in the entire world. Everything is about resource sharing if you think about it. On top of this, if you don't get quality of service and if you don't share resources well in a controllable manner, this makes system management very difficult. So for example, if you're operating a data center and if you provide some service level agreement guarantees to some user, how do you guarantee that service level agreement? You say that you're going to get this level of performance, whatever metric it may be. It may be some request per second. It may be some latency metric, like you get your request satisfied within 10 milliseconds or so, whatever. If you are sharing resources in an uncontrollable manner, some other application that's running on the same hardware can actually deny service to the application for which you need to guarantee some level of service level agreement. Meaning that if you don't have a substrate that provides some fairness and controllability such that you can prioritize the applications for which you need to provide service level agreements, you may not be able to satisfy the service level agreements. And if this is the case, in fact, if you don't have such substrate, usually what people do is they over-provision resources. They say, okay, I have a service level agreement with this customer. They need their request satisfied fast. They're paying a lot of money to us or something like that. And as a result, what they do is they dedicate some servers. Servers may have hundreds of cores. A lot of them may be underutilized or unutilized. And you don't have the capability to provide fairness in those, like in the memory controllers, for example. So you basically say only this customer will run these workloads over here. Now, think about the implications of this, right? This may be like, it's not just wasting resources. Wasting resources always wastes power also. So you provision your data center to be much larger than it really needs to be because you don't have a substrate that enables quality of service control at the lower levels. Meaning that you need to build a much bigger data center. You need to have much bigger power resources. And then in the end, world gets destroyed because you need to have access to power. This is what's happening in these LLM workloads today, actually, if you think about it. Everybody's crazy about these LLMs for good reason or bad. But in the end, if people want like some quality of service when they're interacting with these LLMs, a lot of servers need to be dedicated for them. And even though those servers may not be fully utilized, you cannot run anything else on them because that would really violate some of the service level agreements that people may want to satisfy. It's not just LLMs, it's everything, of course. This is general resource sharing. When we were doing a lot of these work, LLMs were not there. And when people were doing a lot of these quality of service works in the past, clearly LLMs were not there. But today we have a much more power hungry application. That's why I like using LLMs. Okay, so basically in the end, to summarize, sharing improves throughput. It gives you a better utilization of space and bandwidth. Partitioning provides performance isolation. It gives you predictable performance and avoids denial of service and starvation by giving dedicated space and dedicated bandwidth. Clearly, we want both. right? We're greedy. The question is, can we get the benefits of both as much as possible without increasing the cost significantly? So that's what we are going to discuss in the rest of this lecture with a focus on memory controllers. But keep in mind that this is not just about memory controllers. Any shared resource needs to be this way in the end. And the idea is very simple again. We would like to design shared resources such that they're efficiently utilized, controllable, and partitionable. And I believe this is actually a very interesting area because there's a lot more to do in this area right now. Yes? Okay. Yeah, I mean, we're going to discuss that, but if you want to provide some sort of fairness, partitioning, etc., in a place where the hardware is shared, you need to have mechanisms in the hardware. This doesn't mean that it's only hardware. In the end, there needs to be an orchestrator at the higher level, which is the system software, to actually enable what kind of partitioning needs to be implemented. We're going to talk about that basically. But without having mechanisms in the actual shared hardware resources, it's very difficult to do things purely at the software level, because resource sharing, as we have seen last time, happens at nanosecond granularities, and operating system usually kicks in at microsecond or even higher levels, microsecond, if you're lucky, microsecond. Usually it's millisecond level granularity. So operating system cannot react. It may not even be aware of the unfairness that's happening at the underlying levels. That's a good question, though. In the end, it's a really hardware-software problem together. Okay, so basically, we want no wasted resource and also quality of service mechanisms for threads. So how do we get that? Like before we get that, I think this is what we're looking at in this lecture. You have shared memory resources where cores could be accelerators, are injecting requests into, and threads requests interfere here. And this is another picture over here. So basically, I think we have seen some of these slides, so I'm going to go through some of these relatively quickly. But basically, the threads share the memory system, but memory system does not distinguish between threads requests. This is getting better and better over time. Today, we're in 2024, and it's much better. So you can actually distinguish between threads requests and the caches, somewhat in the memory controller, but there needs to be more done over there. So in the end, if you don't have control algorithms that are carefully designed to be thread aware and thread fair, aggressive threads can deny service to others. And existing systems actually don't do a good enough job still on this. But we're going to talk about actually the history of it a little bit as well. So you've seen this picture before. This is actually real results on real hardware, circa 2006 or so. It was published in 2007 in Usenix Security. And basically, we ran multiple applications at the multi-core systems of the day. This is Intel Pentium D. This is MATLAB. This is GCC. And we measured the slowdown each application experienced compared to when it's run alone on the same system. Each of them is using one core. And you can see that one of the applications slowed down very little when they're running together. Another application slowed down by a lot. So clearly, there's some unfairness in the system because MATLAB tended to be very intensive and very streaming. And we have seen in the last lecture that both of these are actually very bad for, let's say, causing trouble to other threads. We're going to look deeper into the problem. And we identified at the time that the problem is really at the memory controller level. And we call this the memory performance hog. And we actually wrote applications that are much more controlled, like streaming and random access applications, and basically showed that because the memory controller prioritizes streaming application almost indefinitely, you have unfairness caused on the random access application. I don't know, I should really get rid of this. Right, floating meeting controls. Okay, much better. And I'm going through this relatively quickly because we covered some of this in the last lecture. This is the streaming application and this is the random application we wrote. You can see that the only real difference between the applications is how they access memory. This is in a streaming fashion, such that it accesses consecutive cache blocks in consecutive memory locations, whereas this application accesses memory more or less randomly. And as I said last time, if you're actually doing micro benchmarking like this, you wouldn't put the random call over here within the loop because random call actually dominates a lot of performance. So you actually pre-generate the indices that you're going to access for both the streaming and random access application, and then use those pre-generated indices to access memory. That way you equalize the time spent in preparing the accesses, such that the only difference is really the access pattern, streaming versus random. You don't want to measure the random random function call here, right? You really want to measure the difference in access patterns. So I keep that in mind. Micro benchmarking or benchmarking is really important. If you do something wrong, you would be measuring that random actually is much worse in terms of performance because because you actually keep calling the random access function. Okay, anyway, I think you have seen this in the last lecture again. What happens when you run these two applications is because the memory controller employs a policy that prioritizes accesses that go to the same row buffer, stream applications, accesses that keep hitting in the row buffer get prioritized. As a result, random access application gets denied service until streaming application stops accessing that row that's in the row buffer. Okay, I could keep doing this. Sounds like fun. I'm proud of these animations that I made at the time. I think it's important to explain concepts with good like animations, etc. You don't want to overdo the animations in general, but I think this explains the concept nicely. Okay. And we have discussed this basically. You may have actually hundreds of requests of one thread serviced before another thread. This may not be the worst case. In fact, this is not the worst case. You can actually construct an access pattern that denies service to the random access application, even with just only one other application running. Right? Stream you may actually, what you may do is actually you may change the caching policy such that you keep evicting stuff from row 0, and streaming application can keep accessing row 0 in memory almost indefinitely, and that could be much worse than what we did. But our goal was not to really construct the worst case. Our goal was really to demonstrate that this is an issue in real systems, and we demonstrated that. We actually published this in Usenix Security, and at the time, there were not that many hardware security papers in security conferences. So the talk I gave was slotted in a session called Low Level. Probably mine was the lowest level talk at the time. Today, if you look at the security conferences, there are much lower level talks like RowHammer, etc., which is interesting, right? So it's good that security folks are more and more open-minded about expanding into security issues that are actually broader than just software. Okay, so I think we've also seen this last time. So why is this happening? This is happening because the memory control policy is not fair. The commonly used scheduling policy is a variant of FR-FCFS, as we discussed last time. It prioritizes row hit requests over others. It prioritizes older requests over others, assuming row hit status is equal. Clearly, this tries to maximize DRAM throughput by exploiting the row buffer locality, and otherwise it's oldest first, which you may argue is fair. I will argue it's completely unfair also. But in the end, it leads to unfairness. We'll talk about the oldest first also in a little bit. And these are actually real results also. This is the stream application, this is the random access application, and you get basically highly disparate slowdowns. Stream application is a good memory performance hog. It denies service to almost everything else it runs with, except for another stream. If you have two streams, then they both slow down equally, as we show in the paper, which are not in the results over here. This used to be Microsoft Virtual Machine, Virtual PC. I don't know if anyone used it anymore, but we wanted to show that this is a problem in real virtual machines also. And this problem becomes worse as you actually increase the number of applications sharing the memory system, because memory system becomes more loaded. And as a result, applications that have characteristics that kind of look like stream deny service to others. As we discussed, this leads to the vulnerability of denial of service. Someone can actually write applications that are malicious in denying service, or some applications may inherently be denying service to others without having malicious intent. You cannot enforce priorities or SLAs. We argued that in the paper also. And we said that this is actually bad for system performance as well. So even if you're optimizing for performance, it's not a good optimization target, because this application, if it's prioritized in the memory system, it's going to go slow anyway, because it's very intensive. And its memory requests are going to go slowly. It's a bandwidth hog in general. By definition, it's going to make progress slowly. It's not going to utilize its cores. If you had actually prioritized some other low intensity application that once in a while generates requests, you could get that request out of the system, and the core that's actually generating those requests could make much faster progress. So for system performance, this is also a bad policy. The policy is really trying to optimize for DRAM throughput, as we have discussed, but that's not necessarily a good goal if you consider the overall system. So basically, this policy, we argued, is good for nothing in the end. And as a result, you have an uncontrollable, unpredictable system. And there are many works that have replicated these results also. So I should also say that this becomes worse if the system becomes a little bit more complex. I'm not going to go through this in detail. We're going to cover interconnects later on. But if you have a system that is, let's say, more scalable, and let's say you have 64 cores that look like this, and you have an on-chip network where the cores communicate with each other or the memory controllers through routers in the on-chip network, packet switch routers in this particular case. You can, again, have applications that are essentially accessing the memory controller over here, over and over with high intensity. And if you do that, it turns out the links, for example, if your routing policy is XY routing, such that this application, when it's accessing this memory controller, it has to go through this link first, X dimension first, and then Y dimension next. This application also goes to X dimension, Y dimension next. The links over here becomes oversubscribed, and applications that are trying to use those links may be deprioritized. And we have shown that you can actually have huge latency increases like 5,000x. These are crazy numbers, but these are real numbers that you can get because the policies that are employed in the routers are unfair. Again. So essentially, if your scheduling policies are unfair, you can get huge slowdowns. And these are the papers that I've kind of covered, but we're going to cover more of this later on when we talk about interconnects, because similar problems happen in interconnects. If you think about it, memory controller is really managing interconnect, right? What memory controller is doing is it's really managing a lot of resources, yes, but in the end, it's managing the off-chip bus, which is really the interconnect. And your scheduling resources, at least the bandwidth management, is done through the interconnect. There's always this debate, which is interesting in memory. Is it the memory? Is it the interconnect? And if you generalize interconnect, is it the communication? Which one is the bottleneck? And my answer is always both, because both are part of the same thing. There's processing that's far away today, and then there's memory and there's interconnect. But if you look at memory, a lot of it is in the interconnect also, as we have seen in the memory lectures. So never think that memory is something that's independent of the interconnect. Memory and interconnect are always coupled together, and they work together. We're going to see more of this when we talk about interconnect. Okay, any questions? Now we're going to see how we solve the problem. I've been kind of motivating the problem. Okay, I like using Maslow, as you can see over here, but I think there's a good reason. So we've kind of said that kind of tongue-in-cheek, what you really care about: robustness, security, energy, performance. Maybe what you really care about is quality of service, right? If you go and get quality of service, if you're starving, that's a real safety and security problem in the end. You cannot do anything else. You cannot even have energy. You're just starving, right? Right? This is tongue-in-cheek, but I think there's some truth to it also. Okay, so how do we solve the problem? Essentially, we want to control the uncontrolled interference that happens in these shared resources. So that means that we need to design an interference-aware or quality of service-aware memory system. And here, there are many questions over here. Basically, I think I'm going to talk about three major things. How do you reduce the interference that happens? Because if you reduce the interference, this is good for performance in general. It reduces the load on the resources that are interfered with. It improves system performance and core utilization, and reduces serialization and starvation, essentially. So reducing is always good. So if you have too much load on the memory system, try to reduce it as much as possible with software or hardware techniques. And we're going to see some of that, especially later on. I don't know, maybe Ataberk will get ready, but let's see. I'm going much slower than I thought. So. Okay, and then the next step is, well, not next step, but all of these can be done concurrently, of course. How do you control the interference that happens? And this is really, how do you provide mechanisms to enable system software to enforce some sort of quality of service policies while providing high system performance, which means that you need to have a fairness substrate, underlying fairness substrate that the system software can rely on and control. And we're going to see that in a little bit. Of course, I think this while providing high system performance is important, because if you provide a fairness substrate that's extremely slow, not good performance, then in the end, it may be better off not to share the resources, right? So you may have a single core running on a 1,000-core system, and that is clearly providing some sort of fairness and some sort of guarantee to system software. But that's not the guarantee that we want. We want, ideally, thousands of cores running together, and while providing some guarantee to the system software. And on top of this, we would like to make this system and memory system configurable and flexible, because in the end, the policies that you want to dictate at the higher level are coming from the user or the system, right? You may want to provide fairness or throughput when needed. You may want to prioritize a particular application when needed. You may want to provide strong performance guarantees to particular applications when needed. And sometimes you may not care. The system software can say, I don't care about any of these applications that I'm running. Do whatever you want underneath. Right? That may be possible, right? Depending on the characteristics of the applications. For example, if you're running the same thread, all of them are streams, the system software may know that, and they say, I don't care, do whatever you want over there. I think in general, that's not a good policy, but it's possible that under some conditions, it's an okay policy. Okay, so we're going to talk about some approaches. I classify these as smart resources versus dumb resources, meaning you have these resources that are shared between threads or applications, and you can design each of these resources to be essentially smart. Smart meaning each resource has some sort of configurable interference control and reduction mechanism. We're going to talk especially about memory controllers today. But a lot of the ideas that we're going to discuss are going to be applicable to interconnects and caches, except you need to design specialized mechanisms for those. But there's another approach to this, which is keeping the resources dumb, which is essentially design the memory controller just like we discussed earlier. It's vulnerable to denial of service. It's doing row hit first and oldest first. But somehow design things around it such that this sort of, let's say, not so fair scheduling policy doesn't hurt applications or systems. So how can you do that, for example? For example, you monitor what's going on in the memory controller, and you basically change which applications can inject requests into the memory controller. Slow down the applications that are going to starve others. Right? For example, you detect that stream is causing a lot of trouble to another application. Tell stream, you're not going to inject more requests to me for a while so that I can service other applications. Right? This is an example of source throttling. You throttle the sources that inject a request to the resources. And this is actually a very powerful approach. This is actually employed in the internet. When you have congestion, for example, in the internet routers, routers can basically send signals to the sources saying that you are congesting me, so you're not allowed to send requests. This is employed at the higher level protocols like TCP, IP, etc. So source throttling is a powerful way. But we will see that it actually has upsides and downsides when we discuss it. You can change the data mapping to memory controllers and also banks and maybe subarrays such that threads don't interfere with each other, right? So one of the issues with stream and random is they interfere with each other in the banks. If you actually allocate different applications to different banks, maybe that interference gets reduced. It's very hard to reduce everything, of course, because at some point you share the memory bus. You can partition the channels. You can partition applications to different channels such that they don't interfere with each other in the channels. That's another possibility. So that's called quality of service aware data mapping, and we're going to see that as well. Also, you can do quality of service aware thread scheduling. So if you actually have control at some level, for example, and if you understand your applications, you can say, I'm not going to schedule applications that are going to destroy each other's performance to the same, let's say, node. I'm going to separate them across different nodes that do not share resources. We can, for example, have this sort of control if you have a data center scheduler. This is a software scheduler. Usually, this sort of control is not so easy. Usually, all of these actually dumb resources approaches have high overheads, especially if you don't have control. And when you have control, they have some undesirable properties. For example, if you partition the channels across different workloads, you're also partitioning physical memory, meaning you may not get all of the physical memory for an application that demands high capacity. Right? So it's good to think about these. Okay, any questions? No? People are very silent. All of these are good. Okay, I see some heads bobbing. Okay, so now we're going to jump into memory controllers, but at some point we're going to generalize. Okay, I guess before we jump into memory control. So essentially, to summarize, there are 4 fundamental interference control techniques. One is prioritization or request scheduling. You can change that. The other is data mapping to different resources. The other is core or source throttling, and the other is application and thread scheduling. We're going to start with prioritization. Other quality of service techniques, if you don't get to it in this lecture, we're going to get to it at some lecture in the future. But if you are not patient, you can, of course, watch prior lectures that we have. And there are a lot of interesting things. We're going to see this load latency curve when we talk about interconnects, for example, but we may actually talk about that in other techniques. Okay, memory channel partitioning. I should also say that we're going to be kind of centric, like processor centric, meaning we're going to talk about how to handle requests coming from different cores. But don't think that that's the only source of interference in the system, right? Cores are generating requests, but there's also I/O subsystem that's generating requests. For example, if one core is trying to get something from the disk, usually the way you access data from the disk is you do memory mapped I/O today. You get a huge block from the disk, it could be 4 kilobytes, and you bring it to physical memory. And the way this is done is through the direct memory access engine today, meaning that there needs to be a request sent to the storage system as well as the memory controller, such that the storage system brings in the 4 kilobyte page or a set of 4 kilobyte pages through the memory controller into the physical memory. Now you can think that there's actually a lot of interference that may be caused coming from the storage system to the main memory, right? While your other applications on other cores are also running. So there's also interference that comes from the I/O subsystem. And I think this is actually one of the large sources of interference today. But we're going to talk about that maybe later on if we have time. But here's a paper that actually has a nice solution to this problem. Okay, I'm going to talk about quality of service over memory scheduling. I've shown you this picture before. The key is how do we schedule requests to provide high system performance, high fairness to applications, and configurability to system software. Remember, when we talk about self-optimizing memory controllers, we just said high system performance. I think going into the future, using machine learning techniques to enable all of these is actually very, very interesting also, but it's a problem that's not solved yet. So to be able to do this, we're going to assume that memory controller needs to be aware of the hardware context or threads that are generating requests. And we're going to tag the request with the hardware context ID that's actually generating that request. It could be a core, it could be an accelerator, it could be a different GPU thread, etc. I'm going to cover a lot of ideas. This is the next 4 slides or so are a summary of the ideas that I'm not going to cover right now, but you can look at it on your own. You can think of this as the abstract of the lecture. But I'm not going to cover it right now. We're going to cover some of them. Actually, to be fair, I'm not going to cover everything that is written over here. For example, how do you handle resources in the presence of prefetch requests? This is actually a very important thing to discuss, but we're not going to discuss that in this lecture. You can read papers related to that. We're not going to cover some of the criticality-aware scheduling mechanisms also. Okay, so let's start. I'm going to talk about the first idea that we developed to solve this problem. I still like this idea, except it's not easy to implement in general. There's more of an idealistic idea, if you will. So you've seen the problem. We have unfairness. If you see this sort of unfairness, one solution is to actually try to equally slow down the threads. And that's the idea over here. When you have threads that are sharing main memory, a definition of fairness is to ensure that threads experience similar slowdowns compared to when they're run alone. Not an unreasonable definition. That's the idea. Each thread should experience similar slowdowns as opposed to these hugely disparate slowdowns. This is actually a nice definition, kind of, because it can also improve overall system performance by ensuring cores make proportional progress. Proportional in the sense that every thread is slowed down somewhat equally. So how do you implement this? Assuming that this is a good goal, which we're going to revise later on in future work. Implementation is not easy. Basically, memory controller needs to somewhat estimate, or somehow estimate, the slowdown of each thread, and schedule the requests in a way to balance the slowdowns. Okay, that's the idea of stall time fair memory schedule. So to be more concrete, we're talking about the DRAM system, and we're going to define a DRAM system to be fair if it equalizes slowdown of equal priority threads. So there are some assumptions over here. If threads are equal priority, you don't want to equalize the slowdowns of complete different priority threads, right? One thread is a lot of high priority to the user. You should prioritize that if you have that information. The difficulty happens when you actually have equal priority threads. And the goal is to equalize the slowdown relative to when each thread is run alone on the same system. Now we've introduced another difficulty over here, which is how do you figure out what is your slowdown compared to when you're run alone on the same system, right? So basically, this is the definition. We're going to define DRAM-related stall time as the time a thread spends waiting for DRAM memory, which is reasonable. It cannot make progress because it's waiting for an outstanding request. we're going to define a metric called stall time shared, which is the DRAM-related stall time of the thread when the thread runs together with other threads. This is easy to collect and understand, right? If a core is stalled when it's running together with other threads, you increment a counter, for example. The difficult thing to estimate is this metric, which is stall time alone. This is the DRAM-related stall time of the thread when the thread runs alone. Now, how do you estimate that? Basically, memory slowdown is stall time shared divided by stall time alone, which really is a metric of relative increase in stall time because you're sharing resource with other threads. So the goal of the stall time fair memory scheduler is to equalize memory slowdown, this metric, for interfering threads without sacrificing performance. So there are multiple things that are good in this metric. It aims to allow proportional progress of threads with this definition of slowdown. It also considers inherent DRAM performance of each thread by actually dividing the shared stall time with the alone stall time. For example, if your alone stall time is very low, your shared store time should also be low in that sense, right? To get equal slowdowns with another thread that has a high alone stall time. For example, if a thread stalls for 10 seconds when it's running alone, and another thread stalls for 1 second, clearly the thread that stalls for 1 second has inherently high performance. That's the assumption. It's not bottleneck, it's by memory. You want to slow both of them by, let's say, 2x. That means the thread that is stalled for 10 seconds when it's running alone, it should be stalled by about 20 seconds when it's running together. The thread that stalls for 1 second should be stalled by 2 seconds, right? So 20 divided by 10, 2 divided by 1, they're both slowed down by 2x. But the overall absolute impact is really 10 seconds on the thread that inherently is slower. And this is the definition of fairness. You could argue that this is good or bad, but this is the definition that we're going to try to enforce. And this gives something to the system software to work with, right? The system software can clearly understand the implications of this. I'm going to slow down each thread equally, meaning a thread that is already slow is going to be impacted a lot more in terms of absolute stall time, right? That's fine. Now the system software can deal with it. Yes? Mm-hmm. Yes. We're going to talk about that. Yes, that's one way of estimating it. Basically, collect the data when you're running alone, run the thread alone, and then figure out what's the stall time alone, and then run the threads together. But if you actually try to estimate stall time alone separately for each thread by running them alone, that has actually a lot of impact on throughput. You don't want to do it that way. I agree with you. That's not a good way. Yes. Okay. Yes, current. That's right. Yeah. Yes. Mm-hmm. We're going to talk about that in slide 120 or so. Basically, yes, that's a very good question. The assumption in these works right now is to treat cores independently, such that they're running independent threads. If the threads are actually interdependent on each other, because they could be part of a multi-threaded application where the threads are coordinating, then you need to take a slightly different approach. And we will see that you could actually modify some of these mechanisms to also improve those applications, but we need to come back to that. Let's solve the easier problem first. Okay, very good questions in the end. So the question is basically, how do you estimate ST alone in the end, right? For each thread, the DRAM controller tracks ST shared. This is easy to do because you know exactly when you're stalling, when you're sharing resources. You just count how many cycles you're stalled, right? Actually, this requires some coordination with the core also. You cannot do it purely at the memory controller, but read the paper for more. The difficult part is ST alone. So we actually, and this is what makes this algorithm complicated. Later work actually found a way of estimating in a better way. And my PhD student, Lavanya Subramaniam, developed a technique called MICE, which is actually trying to estimate this in a much better way by looking at the request rate that goes into the system. But we're going to talk about that later. In this incarnation of the work, the memory controller does the hard task of really computing the slowdown. It basically figures out what's ST alone. So one way of figuring out ST alone is, the basic idea is, you know ST shared. Figure out ST alone by computing another metric, which is excess stall time. And this excess stall time is the stall time that you've experienced because memory controller preferred some other thread over your thread. And you could actually have some idea of this. So memory controller keeps track of all the resources. It can say, oh, in this bank, the thread A has a request, thread B has a request. I scheduled thread B over thread A, which means that I actually caused some delay to thread A. So increment ST excess meaning excess, extra stall time, by some amount. The question is by what amount? What amount is the difficult part because some of that latency could be overlapped by other requests. It may not directly impact the thread that's delayed as stall time. But this paper describes how to estimate it, and it has some somewhat reasonable estimations. But memory controller can keep track of the resource. In the end, ideally, if you want to estimate this ideally, you need to run another copy of memory controller that actually is running the thread alone. But we don't want to do that at the same time, right? Clearly, that's expensive. So if you read the paper, you will see that you need to estimate the excess stall time. And excess stall time may happen because you preferred some other request from some other thread over this thread's request. Row buffer conflicts are another problem, right? You preferred some other request from some other thread and caused a row buffer conflict to this thread. And then you need to estimate that also. So now you can see that things are getting a bit hairy. How do you estimate that this thread was delayed because you started scheduling a write request from some other thread and the memory controller switched to a write mode, whereas it could have been in the read mode if this thread was the only thread running in the system. So this paper punts on some of the issues. It doesn't estimate everything perfectly. Okay, but actually assuming that you have some sort of estimate, the memory controller computes some unfairness value, which is the maximum slowdown of any thread in the system, divided by minimum slowdown of any thread in the system. And it basically has a threshold. If this unfairness value is less than some tolerable unfairness, which could be determined by the system software, then the memory controller uses the existing DRAM throughput-oriented scheduling policy. Everything is good. If unfairness is intolerable, basically the memory controller switches to a simple fairness-oriented scheduling policy where it prioritizes the request from the thread that has the maximum slowdown first. Again, this is a prioritization policy. If there's a request from a thread that has a maximum slowdown, prioritize that. Otherwise, prioritize row of hits. Otherwise, prioritize the oldest first. Okay? So let's take a look at how this works with a picture again. Assume that we have two threads, thread 0 and thread 1. Thread 0 is the bad thread. Essentially, it causes unfairness. It keeps accessing row 0. When thread 1 has a request that essentially gets deprioritized, the memory controller increases the slowdown of the thread whose request gets deprioritized, as you can see, right? Thread 1 could have been scheduled, but the memory controller preferred thread 0. As a result, thread 1 slowdown increased and unfairness increased. But this is still acceptable, as you can see. We've set alpha, which is the unfairness threshold, to 1.05. Now, the memory controller keeps doing, because its unfairness is tolerable, it sticks to the throughput-oriented policy, which again delays thread 1's request, and thread 1 slowdown increases. And now unfairness becomes intolerable, as you can see, greater than the threshold. And then the memory controller switches to the fairness-oriented policy, where it picks thread 1's request as opposed to thread 0's. So now we've broken the row hit first policy, as you can see. Now this causes slowdown to thread 0 compared to when it's running alone. You need to keep track of that because it actually switches the row buffer, for example, and thread 0 slowdown increases, which reduces the unfairness to an acceptable level. The memory controller switches to the throughput-oriented scheduling policy. In this case, it's oldest first because nobody has a row buffer hit, and this happens to be the oldest, which switches the row buffer again. And it causes slowdowns to both in this case, because this request to row 0 experienced a slowdown because it actually was a row buffer conflict, and this experienced a slowdown because it was delayed. One of the requests was delayed. But still, unfairness is tolerable in this particular case. And then the memory controller keeps sticking to the throughput-oriented policy, which again increased the slowdown of thread 1 and increased unfairness above an tolerable threshold, which means that the memory controller switches back to the throughput-oriented, fairness-oriented scheduling policy and keeps fairness under check. So we could keep doing this for a long time, as you can see, but hopefully you got the idea. The memory controller by tracking slowdowns and trying to keep unfairness within an acceptable threshold, it switches back and forth between fairness-oriented and throughput-oriented scheduling policies, which looks nice on paper, as you can see, not easy to implement, expensive, basically. Okay, yes. How can the performance of the system? Basically, it's a system level performance. You may have, I think the short answer to your question is memory bandwidth is not equal to performance. So some thread, for example, that is not very intensive, which is not the case in the previous example, may be delayed behind another thread that has hundreds of requests. Now you prioritize that thread that has one request, and the thread keeps making progress in its core. As a result, overall core utilization increases. Make sense? Yeah, I mean, these papers don't deal with energy, but overall, if you improve performance, usually energy also improves, but not necessarily, because row buffer conflicts may increase, yes. So in general, this sort of fairness-oriented policies are not a reduced memory throughput, because they want fairness. They could improve performance, not in all cases. In some cases, performance reduces, as you will see in the papers also. Energy is not evaluated, but my gut feeling is that on average, energy is better also, but it needs to be evaluated. My favorite example of, we've talked about row hit first, right? Let's talk about oldest first. Is that a good policy for fairness? Anybody? Anybody try to go through Tannenbaum's revolving doors? It employs an oldest first policy. So I'm one thread, and then there's another thread that has a group of students, 100 students who want to get food. I'm on my own thread. I'm trying to get to class. Those 100 students happen to arrive slightly before I arrive at Tannenbaum's revolving door. What happens? I'm late to class, right? This is the oldest first policy. And you can see that oldest first policy is completely unfair. And there's no row buffer here. It's just revolving, right? It's oldest first. Okay, so I think we've established that oldest first is bad also for fairness, as you can see, right? It prioritizes implicitly intensive threads. You keep generating requests, oldest first works for you. You don't generate a lot of requests, which is the right thing to do. Don't generate a lot of requests, right? You keep the memory bandwidth, save the memory bandwidth. It's expensive for many reasons. You get penalized. Okay, so going back to STFM, upsides. This is actually the first algorithm specialized for fair multi-core memory scheduling. There are prior works in this area, but they actually don't treat memory scheduling as a memory controller problem. They treat it as a router type of problem, which this paper shows that it shouldn't be treated that way, because there's bank parallelism, and there's also locality in the memory controller that need to be considered. It provides a mechanism to estimate the memory slowdown of a thread, which could be useful if it's exposed to the system software. And the paper talks about how to expose it to the system software, which I'm not going to talk about. It's good at providing fairness, and being fair can improve performance, as we have discussed, and the paper shows that actually. Now, the downside is, there are a lot of downsides. One is it doesn't handle all types of interference, as we will see in a little bit. It's complex to implement. We kind of solved this problem in the HPCA 2013 paper, Mice. If you're interested, you can read that. It's part of Lavagna's thesis. Slowdown estimations can be incorrect, in fact, wildly incorrect, as we have shown that also. But that may be okay if your goal is to actually improve performance and fairness. If you really want to enforce a particular amount of slowdown, you really need to be much more accurate than this. So this may not be good for enforcing some performance or slowdown guarantee, but this may be okay for improving fairness. Okay, and that's the paper. This is part of your recommended reading. Any questions? That's the first attempt. I'm not suggesting this is the best attempt, but I think this is a deep work that talks about how to actually provide fairness. Since I need to get to the airport, so I'm going to cover one more thing, and then we'll take a break and we'll see how we handle things. Or should we take a break quickly? Thoughts? Who votes for a quick break? Raise your hand. No one. Who votes for continuing? Okay, I see more votes, sorry. but we're going to take a break after this. Okay, let's talk about the second attempt. I like the second attempt. In fact, the second attempt was implemented in some of the SoC controllers designed by Samsung. Some people at Samsung actually read our paper. They said, oh, there are good ideas here. Let's implement it. And variants of them were implemented. I like some of the observations over here. So let's basically, while we were looking deeper into the problem, we discovered that there are other issues that actually, in my opinion, are broader. Let's talk about one of the issues. Basically, we have discussed that one way of tolerating the latency of different requests is to generate multiple outstanding requests. Right? You have out-of-order execution in processors, non-blocking caches, run-ahead execution. Some of these things we will see. These all try to exploit memory-level parallelism. They try to, whenever you have one request, these try to overlap multiple requests, latencies, so that the processor doesn't stall for a single request over and over and over, and you stall once for all of those requests. I'm going to show this in more detail. Now, these are effective only if the DRAM controller actually services the multiple requests in parallel in DRAM banks. First of all, there are multiple conditions that need to happen. These different requests need to go to different banks, right? If they go to the same bank, then you cannot parallelize those requests. That's what we tried to solve with the subarray level parallelism paper, right? If you remember. If they go to the same bank but to different subarrays, you parallelize them, ideally. So you can see now the connections between different works. Right? And we would like to do that. Assuming that they go to different banks, still, if your memory controller is not doing the right thing, you may not be able to service things in parallel. So basically, multiple threads share the DRAM controller. And unfortunately, DRAM controllers may not be doing the right thing. They may not be aware of the parallelism in each thread's requests. As a result, they can service each thread's outstanding request serially and not in parallel. So let's take a look at an example. So we're going to look at a single thread over here, thread A. It computes. It generates 2 DRAM requests. They happen to go to different banks, which means that the memory controller receives the first request, starts accessing bank 0, and then things stall, of course. The memory controller then starts accessing bank 1, and these 2 requests are serviced in parallel. Right? So everything looks reasonably good because you don't stall once for each request. You parallelize the bank access latencies of the requests. And if bank access latency is the dominant part of the access latency, then most of the access latency is parallelized. So essentially, the thread stalls for approximately 1 bank access latency, which is good. Ideally, this is what you want to have. Okay, let's take a look at how a baseline scheduler may do badly when you're running 2 threads together. 2 threads are going to do exactly the same thing. They're both going to compute, generate 2 DRAM requests each. These will arrive at the memory controller in this order, let's say. Let's assume that the memory controller services them in the order that's shown over here. It first takes thread A's request, schedules it to bank 0. Both threads stall. And then takes thread B's request, schedules to bank 1. Both of them continue to stall. And then thread A's request to bank 0 is done. Thread B's request to bank 0 is scheduled. Threads continue to stall. And then thread B's request to bank, thread B's request to bank 1 is done. And then thread A's request to bank 1 is scheduled because we're going through this order. And both threads continue to stall. Essentially, what happened was, even though each thread had 2 requests to 2 different banks, because the memory controller did not order the servicing of these requests such that each thread's request would be serviced in parallel in the different banks, both of the threads had their requests serialized at the memory controller. And on average, each thread stalls for approximately 2 bank access latencies. Right? The question is, can you do better, right? And this is only 2 banks, 2 threads. If you actually increase the number of threads, things become worse. And the paper is an example of that. Let's see how you can do better. If you had a slightly more intelligent memory scheduler called Parallelism-aware scheduler, it receives the requests in the same order, same threads, nothing has changed, same banks, etc. Then the memory controller first picks, let's say, thread A's request to bank 0. Instead of going and taking thread B's request to bank 1, the memory controller would say, can I parallelize this request with another request from thread A? And it basically discovers that there's another request from thread A to bank 1, and it picks that one next. This parallelizes thread A's requests. Thread B is not serviced. Kind of it stars for a while, fine. And then thread A's request to bank 0 is done. the memory controller picks thread B's request to bank 0, and then thread A's request to bank 1 is done. The memory controller picks thread B's request to bank 1 and serves them in parallel. But what happened was thread A's request got completed because they were parallelized. So thread A can go back to its computation. Now thread B, unfortunately, stalled the same amount, and at some point it gets its request back and it continues to compute. So the net result is we've accelerated thread A by saving cycles without hurting thread B. So overall, by exploiting the bank level parallelism and having a memory scheduler that's aware of the parallelism of each thread, we can improve performance, as a simple example suggests. And the average stall time in this case, you can do the calculations, 1.5 bank access latencies. Right? Does that sound good? So this is another example of memory controller being aware of what's going on at the core level, right? Before we were talking about memory controller and caches being aware of each other. In the end, I think we need to make systems aware of what's going on, which requests are important, which requests can be parallelized. Okay, so how do you design a memory controller that looks like this? So our goal was to actually exploit this observation to improve performance as well as fairness. As we will see, this also improve fairness. But we will also have other mechanisms to improve fairness. So the parallelism-aware batch scheduler has two principles. One is parallelism awareness, which is what I just described, but I'm going to make it more formal. If you want to exploit or preserve each thread's bank level parallelism, you want to schedule a request from a thread to different banks back to back. This really is good for parallelism of that thread. We're not talking about which thread you pick first. We're going to talk about that later, because that has some effect on the parallelism also. But one problem with this is this can cause starvation. You keep servicing this thread's request back to back. At some point, the thread keeps generating more requests because there's a core generating these requests, right? If requests get serviced, the core will continue generating requests. And you don't want to cause starvation. You don't want to be servicing only the thread's request. So to avoid starvation, we have a mechanism called request batching. And this idea is relatively old. It was actually employed in disks to do batch scheduling in disks. Because when you actually have requests from different threads that go to a disk, how do you provide fairness is a problem. We actually employ the same idea of request batching. And the idea is very simple. You group a fixed number of oldest requests from each thread into a batch. You service this batch before all other requests. And you form the memory controller. When you say you, it's the memory controller in this case. Put yourself in the shoes of the memory controller. Always a good thing. The memory controller forms a new batch when the current batch is done. Now, if you have this approach, this eliminates starvation because you guarantee that there's no reordering across batches, right? This provides fairness also. And this also allows parallelism awareness within a batch. So let's take a look at this pictorially. We have two banks again. In this case, we have 4 threads. Assume this is the distribution of requests that are waiting in the request queue from different threads, color-coded. And the memory controller happens to pick thread 0. Memory controller forms a batch first, saying that it's going to service requests from this batch first. It's not going to reorder another or outside batch requests over the requests over here. It'll take thread 0's requests and service them in parallel. Thread 2 keeps generating requests, as you can see, but they don't get included in the batch because we formed the batch. And then thread 1's requests are serviced in parallel. And then thread 2's requests in the batch are serviced in parallel. And then thread 3's requests in the batch are serviced in parallel. And then the batch is done, the memory controller moves to a new batch. Okay? This way you guarantee the batch is done before you actually do any kind of reordering across the batches. So this provides a nice substrate. There could be better substrates. We're not going to deal with it right now. So let's talk about these two components. So request batching is relatively simple. Within batch scheduling is going to be interesting also. You can do parallelism-aware, but also other kinds of request scheduling mechanisms here. So how do you do request batching? This is relatively easy to implement. Each memory request has a bit associated with it. We'll call it marked bit. To form a batch, the memory controller goes through the requests in its queue, and it marks up to a cap, a threshold of oldest request per bank for each thread. This threshold is determined statically, but it could change dynamically also. Marked requests constitute the batch, and the memory controller forms a new batch when no marked requests are left. Okay. And batching is accomplished as a prioritization order. If there is a marked request to a particular bank, that marked request is prioritized over unmarked ones. Okay? There's no reordering requests across batches, which means there's no starvation and high fairness. Then the question becomes, how do you prioritize requests within a batch, meaning within mark requests. So this is where actually things get more interesting. Within batch scheduling, you can use any existing DRAM scheduling policy, actually. You can use FR-FCFS, which exploits robot for locality. And the paper shows that you actually improve performance and fairness, even if you use FR-FCFS, but that's not the best policy. But we also want to preserve intra-thread bank parallelism, as we have seen, right? If a thread has parallel requests to different banks, we want to service each thread's request back to back. So to be able to do this, we introduce a component that's relatively high overhead. It's to schedule or compute a ranking of the threads when the batch is formed. And we prioritize higher ranked threads over lower ranked ones. This improves the likelihood that requests from a thread are serviced in parallel by different banks, because different threads are prioritized in the same order across all of the banks. The rank is the same across all of the banks. You may ask, what about the rank across different channels? Yes, across different channels, you may want the same rank also, but this requires communication across memory controllers, and that is talked about in a later paper. Okay, the question is, how do you compute this ranking? And there are many ways of computing this ranking. So in a sense, now you can see that this batching forms a substrate, a framework, in which you can play a lot of tricks with memory scheduling, right? Because batching guarantees there's no starvation and some level of fairness. Within the batch, you actually can play a lot of tricks with scheduling. So what are those tricks? Let's take a look at those tricks. So assume that these are of the same batch. You have two different threads. If you actually prioritize, the different banks prioritize different threads, both of the threads stall for two bank access latencies. We've seen this before. If you do a ranking, let's say you rank thread A over thread B, or thread B over thread A, it doesn't matter in this particular case. This is what you do essentially, reordering. And thread A's requests get prioritized, thread B's requests get deprioritized, and you save cycles in thread A without hurting thread B. So this is the benefit of ranking. It really achieves what we were trying to achieve earlier, right? So we want to rank. So how do you rank? This affects system throughput and fairness. Ideally, our goal is to maximize system throughput while minimizing unfairness, right? And still, we're using the definition of equalizing the slowdown of threads for unfairness. So how do you maximize system throughput? From the memory controller's perspective, ideally, you would like to minimize the average stall times of a thread within a batch. Again, we're looking at within a batch. Across the batches, there may be different policies, but we want to restrict ourselves within a batch. And if you really want to improve throughput within a batch, minimize the average stall time threads experience. This makes sense, hopefully. Minimizing unfairness is a little bit tougher to reason about, but the insight is that if a thread has inherently low stall time, finish them early in the batch, right? And the reason we do this is because if you delay a memory non-intensive thread or inherently a thread with an inherently low stall time, they would experience a high slowdown compared to another thread that's intensive. This is similar to what we have discussed earlier. If a thread baseline stall time, inherent stall time is 1 second, if you delay it by 2 seconds, its slowdown will be 3x. If another thread baseline request service time or stall time is 10 seconds, if you delay it by 2 seconds, its slowdown would be 1.2x. So if you have a choice between two threads to delay the one that is less intensive, meaning the one that has low stall time to begin with, because the impact of that delay will be much lower on that thread if you have done otherwise, compared to if you've done otherwise. Does this make sense? Okay, so that's the insight. This may not be the best solution because things are very dynamic, as we will see. But this, in the end, this leads to a shortest stall time first ranking, shortest job first ranking, which has actually very nice properties. If you have, there's theory behind shortest job first ranking to maximize throughput in a single server queue. And people have developed this for example, production in factories. If you actually need to produce things in factories, and if you want to maximize throughput, you prioritize things that take shorter to manufacture, for example. That way you actually maximize the throughput overall. So we're going to employ a similar ranking because it actually satisfies both of these in the end. Think about shortest job as shortest stall time first. We're going to estimate the stall time within the batch of each thread, and we're going to rank threads with shorter stall time higher. So let's take a look at an example of this. So we call this the shortest stall time first ranking. We're going to consider two metrics. The maximum number of mark requests to any bank that each thread has. This is called max bank load. And we're going to rank the thread with lower max bank load higher because we expect that lower max bank load leads to low stall time. And as a tiebreaker, we're going to use total number of mark requests, total load, rank the thread with lower total load higher, assuming max bank load is equal. I think this is best seen with an example. Let's take a look at this example. So these are the requests that are from 4 different threads. They're imbalanced right now. They're not equal, to show what is the good thing to do. There are 4 banks. Let's take a look at thread 0, max bank load. Thread 0's requests are highlighted here. The maximum number of requests it has to any bank is 1. So its max bank load is 1, total load is 3. It has total 3 requests. Let's take a look at thread 1. Thread 1's max bank load is 2, meaning it has a maximum of 2 requests to any bank. In a sense, its stall time is likely to be higher than thread 1, right? Because thread 1 has a max bank load of 1. And the total load of thread 1 is 4. Let's take a look at requests of thread 2. Thread 2 has a max bank load of 2 here to bank 1 and bank 2, and a total load of 6. And finally, thread 3 is the most intensive one. It has a max bank load of 5 to bank 3 and a total load of 9. So the expectation, which may not be completely accurate because of row buffer, etc., but the paper talks about row buffer, etc., in the paper. Expectation is that thread 0's stall time is the lowest in this batch. Thread 3's stall time is the highest. So the memory controller should rank thread 0 higher than thread 1, higher than thread 2, higher than thread 3. Thread 1 and thread 2 ranking is determined based on the tiebreaker total load. The expectation is that assuming you have equal number of requests, maximum requests to any bank, your stall time will likely be dominated by the total number of requests you have. That's the idea. Again, these are heuristics. These are not perfect, right? If you really want perfect stall time estimation, it's expensive, as we have discussed in stall time fair memory scheduling. Okay, so let's take a look at what this would achieve in this batch, in this example. So this is the baseline scheduling order that we have. Now I'm going to have a timeline. I'm going to say, assuming we follow this baseline scheduling order, first come, first serve, if we use the same order, thread 0's last request will be serviced after 4 time units. I'm ignoring the bus delays, etc. over here. To a forced order, thread 0 will stall for 4 time units because we basically schedule the request first come, first serve. Thread 1's last request is also serviced after 4 time units, as you can see over here. Thread 2's last request is serviced after 5 time units, and thread 3's last request is serviced after 7 time units. And the average stall time you can compute, it's 5 bank access latencies or 5 time units, okay? Now, if you use parallelism-aware batch scheduling with the order that we have determined when you actually form the batch, this is the ranking, we're going to pick and prioritize thread 0's request first. So the scheduling order would look like this. Thread 0's requests are serviced in parallel, as you can see, in the first time unit, and thread 0 stalls for 1 time unit, which sounds already very good for thread 0. Thread 1's requests are scheduled, the last request is scheduled after 2 time units. We don't waste bandwidth, as you can see, because there's no request from thread 0 over here. Thread 1 is prioritized over everything else, so thread 1's request, first request is sent in the first time unit. You can think of this as playing Tetris, right? You look at thread 0's requests as a bundle, and you schedule them first, and then you put the other Tetris piece of thread 1 that doesn't look like this if you look at this order, but if you have a different way of looking at things, it has a piece that looks like an L shape over here, as you can see. So now thread 1's last request is scheduled after 2 time units. Now thread 2 is the next one to be prioritized, and it is scheduled that its schedule looks like this, and its last request is scheduled after 4 time units. Now you can see that all of these threads gain performance. And because I constructed this example really nicely, no thread loses performance. So thread 3's last request is scheduled after 7 time units over here. So assuming this is the within batch schedule, you've gained a lot of performance. We reduced the average bank access latencies to 3.5 without changing any request, right? We just changed the scheduling order. And this led to about a 30% average improvement. In some cases, thread 0's performance improved by 4x, as you can see in this batch. But remember, this is within a batch. Across batches, you will lose performance because there will be, you're not considering reordering across batches. And you can read the paper for more information on that. Okay, so this is the scheduling policy we came up with. In the end, we wanted to keep the scheduling policy simple, so it becomes a prioritization order. Unfortunately, it's a fixed prioritization order. So marked requests are prioritized over others. This is essentially batching. Within batch scheduling, we are parallelism aware. We still prioritize row hit requests over others. You can say that this goes against parallelism. Yes, I agree. Unfortunately, it does. But it turns out this is actually better for performance on average. This is always a problem. There's locality that you want to exploit in the row buffer. There's parallelism that you want to exploit so that you overlap latencies. Which one is more important? It really depends on the applications, etc. So we schedule higher ranked threads first, shortest stall time first as the next order. But the paper evaluates a different policy where 2 and 3 are swapped. That is almost the same performance as this policy that I'm showing over here. And among everything else being equal, oldest requests are prioritized over others. So this has 3 properties. Now we exploit not only row buffer locality, but also intra-thread bank parallelism to overlap latencies. This is work conserving. This is actually very important, meaning we don't, if we have bandwidth available in a bank, we don't leave the bank idle. If there's an unmarked request to a bank without marked request, we schedule the unmarked request. So we don't waste bandwidth. And importantly, marking cap is actually important. If you have a too small cap, meaning that means that you have smaller batches, and this hurts the row buffer locality. Because if you have a larger cap, you have larger batches, and the probability that for a thread that has high row buffer locality, you will have more requests in the batch. So you can exploit row buffer locality nicely within that batch. Now, if you have too large of a cap, what happens is you put too many requests into the batch, and memory non-intensive threads are likely to be penalized because memory intensive threads are likely to hog and inject a lot of requests into the batch. Right? So there's unfortunately this tension between row buffer locality and also parallelism exploitation, which is not written here, and also prioritization of non-intensive threads. So it's not the perfect policy, but it has these trade-offs, and it's important to understand these trade-offs when you have a scheduling policy. There are many more trade-offs that are analyzed in the paper. So you can ask about the hardware costs. It's a lot easier to implement compared to stall time fair memory scheduling. The paper discusses that. There's no complex operations like we had in stall time fair memory scheduling. But we're going to revisit the hardware costs later because it turns out this is still expensive. Especially if you think about the memory controller as kind of a servant to the processors, right? If you think about the memory controller as a computational unit, maybe this is not that expensive actually. Okay, so these are the results. I will not go through this in detail, but you can see that this is the development of memory scheduling policies. PAR-BS improves fairness or reduces unfairness. Even with this definition of unfairness, we're going to redefine unfairness later on. And it also improves throughput. This is a throughput metric for a multi-core system. You'll read this harmonic mean speed up in the papers. There are multiple throughput metrics, but this is one throughput metric. And you can see that the performance also improves. There are two major reasons for performance improvement. One is we actually reduce stall times because by making the memory controller aware of bank parallelism of each thread, so that you can actually overlap the latencies. That's one reason. And the second reason is you improve fairness. Improving fairness, again, based on what we discussed earlier, enables better core utilization. So it also improves performance. So there are 2 reasons why the performance actually improves. And the improvements may not look that large, but these are actually across many simulations. Okay, let's talk about the upsides and downsides, and then we'll take a break. So this is actually the first scheduler to address bank parallelism distraction across multiple threads, which is actually a very interesting observation. Interestingly, the reviewers were very open-minded when they reviewed this paper. They said, this is a great idea. And they basically said, this is the first time I'm seeing something like this, meaning the memory controller considering what's happening in the core and trying to not destroy what the core is trying to do, right? Because actually cores are designed very heavily to enable memory level parallelism. You go through all of this pain in the cores such that you design this out of order execution window such that you generate more requests to memory. Now you design this core, but if your memory controller does exactly the opposite of what you're trying to do, then you're wasting effort across the entire system. So I think it's important to realize this sort of inefficiencies in the system and try to avoid, enable coordination across multiple components. So it's a much simpler mechanism compared to STFM. Batching provides fairness. Batching can be used independently, actually, which is also interesting. Later works did that. And ranking enables parallelism awareness. Now, the downside is there are multiple downsides. Ranking is actually still complex for some definition of complex. It has also some undesirable behaviors that we will get into. And it doesn't always prioritize the latency sensitive application. So if you think about batching, batching is actually, I'm not going to say that it's very bad, but it's undesirable because if a less intensive core generates a memory request and it happens to come after the batch is formed, it has to wait until the batch is done, right? At least until all of the mark requests to the bank is gone. So you may get unlucky as a latency sensitive or low memory intensity core. And this is the problem that we're going to try to solve in the later works in a hopefully better way. Okay, this is the paper. If you're interested, it's going to be part of the reading. And this is the top picks version, it's a shorter version if you're interested. Any questions? No? Yes, please. Hmm. Hmm. Yeah. Hmm. Yeah. Yeah, I mean, that's a very good question. Basically, in the paper, we look at static batch sizes done empirically, but I agree with you. In the end, it really needs to be dependent on the workload, potentially the application, but that's an area that we did not really investigate further. And that's one of the difficult parts of the mechanism in the end. Any other questions? Okay. Otherwise, let's take a break until, let's see, let's do 14:52. 14 minutes, not bad. And then we'll be back. Hey, Constant. Good. How are you? Okay. Okay, let's get started. Is everything okay online? Yeah. Okay, now we covered two major ideas. We're going to cover some more, and we're going to try to make things like both different and also easier to implement. I'm not going to talk about this one a lot, but this is actually a very interesting work that discusses like how to do the scheduling from a theoretical perspective as well. Here, we're going to kind of ignore fairness. Our goal, we wanted to also understand like what do you want to do to maximize system performance? And the idea that we develop in this work is to prioritize a thread that has so far attained the least service from the memory controllers. The thinking is that if the thread has attained a lot of service, it's going to demand more service, meaning it's very intensive. And if it has attained less service so far, it's likely that it's deprioritized and it also doesn't demand service. So prioritize that thread that has attained less service. So the paper has a lot of theoretical analysis actually on access patterns and basically introduces this notion of adaptive per thread least attained service scheduling. And the idea, again, we're going to use the notion of ranking to preserve parallelism. And we're going to rank threads based on attained service in the past time intervals with some weighted ranking. And enforce the thread ranking in the memory scheduler during the current interval. So this actually solves another problem, which is how often do you change the rankings, right? That was a problem with the previous paper that we didn't discuss in more detail. There, the ranking needs to be computed every time you form a new batch, right? Which means that if you actually have multiple memory controllers, you're really not coordinating between them, right? Whereas here, if you actually form the ranking, let's say every 10 million cycles or every 1 million cycles, etc., then you're doing it at a coarser grain, and you can compute the ranking in a coordinated manner across different controllers. Or maybe there's less need for that. If you read the paper, you will see what I mean. So why does this work? Aside from the theoretical benefits of least attained service scheduling that I'm not going to get into, what this ends up doing is it prioritizes memory non-intensive threads or light threads that are more likely to keep their cores busy, which was our argument for improving performance early on. So if a thread didn't attain service so far, prioritize it so it attains service. And if a thread is very intensive, it keeps attaining service, getting service from the memory controller. And at some point, its ranking is going to reduce. Whereas if a thread is not very intensive, it's going to be serviced, and its ranking is never going to reduce because it's not going to send a lot of requests. It's not going to get a lot of service from the memory controller. Does that make sense? Its requests are not going to be scheduled. So in a sense, it has this nice balance. But this attained service by itself doesn't take into account fairness. It's really for improving memory system performance. I will not go into detail. The details are in the paper, which is going to be an assigned reading, again, part of the homework. But it turns out this is very good for performance compared to all of the other prior schedulers that we have discussed. I like this figure, this again in simulation across many workloads, across 24 cores and different memory controllers. If you have 24 cores running 24 independent threads, having 4 memory controllers is reasonable, and the performance improvement we get over the best prior scheduling algorithm, which is PARBS, which we have discussed, is about 8%. If you starve the system such that it has very little memory bandwidth, you have only 1 memory controller, 1 channel, the performance improvements actually are much higher, as you can see. If you have ample bandwidth, very expensive system, 24 cores and 16 memory controllers, the performance improvements are much lower. This is kind of expected, right? If memory bandwidth is not that big of a problem, a lot of the memory controllers start performing similarly. If the memory controller is a big problem, such that the memory bandwidth is very low, then there's huge differences between memory controllers or memory scheduling policies. But I would say this is not a very reasonable or balanced system, because having 24 cores and having only 1 memory controller, 1 channel, is really starving the bandwidth. As a result, some of the, for example, PARBS doesn't perform as well as STFM in this case, right? It's hard to explain that in general. All of the other configurations, PARBF is better than STFM, for example. Okay, this is another picture that's also nice, again, based on simulated results compared to PARBS. With a system that has 4 memory controllers, performance is always better, as you can see, on average. Again, as the number of cores increases, Atlas's performance benefit also increases. And the paper has a lot more information that you can go into. It's actually a lot of nice graphs, and you can take a look at it. So the upsides of this is good at improving overall throughput. Compute-intensive threads are nicely prioritized over memory-intensive ones. And it's very low complexity. This was also another target that we had. Basically, each thread needs to have an attained service counter, which gets incremented independently of other threads. No ranking computation, etc. Well, it's not. There is a ranking computation, but you can actually increment these counters relatively easily. And also, coordination among controllers happens infrequently, if it happens at all. Unfortunately, this doesn't take into account fairness, which is going to be important in the next work, based on the insights that we develop over here. So some threads that keep getting lower ranked or medium ranked, they get delayed significantly. They cannot escape. They kind of cannot escape from the situation where they're kind of in the middle. The least intensive threads consistently get prioritized, so that's good for performance. The most memory intensive threads usually consistently get deprioritized, but the middle threads, there's no provision for them in a sense, right? They keep getting delayed significantly, and as a result, this leads to high unfairness. But again, this may be a not bad controller to build, and you can read more about it. But we would like fairness and performance, so our next goal was to actually achieve the benefits of Atlas as much as possible while also providing high fairness. Any questions? I've gone through Atlas relatively quickly, but you can read the paper. Okay, so the realization that we ran into after looking into a lot of these algorithms is that in the end, a lot of the algorithms are biased. And we wanted to try to eliminate that bias as much as possible. Again, a machine learning controller may do better than a human controller, assuming it's designed or set up nicely, but we don't know that yet. So here we show the system throughput across many workloads and a reasonable system on the x-axis, and fairness on the y-axis. Here we actually look at fairness from the perspective of maximum slowdown. So previously we said max divided by min slowdown. In a sense, that's not a really nice metric, because maybe we don't really care about the minimum slowdown in the system, right? Why do I care? If I don't slow down a thread, that's good. What I really care about is the bound on the slowdown that I put, right? What is the thread that is affected the worst? If you bound that lower and lower, then the fairness in the system is probably better and better. What's going on? This is low battery, so it's going to die soon. It's the same problem we had before. And I don't want that to happen. It works. It still says low battery. Maybe it's gone. So how do we do that? Let's see. I think it's charging now. Okay.
Yeah, it's charging.
But I need to share again. Okay. Is it good? Oh, what is this? New slideshow. Okay. User error again. So that's why Ataberk knows how to deal with this. He used a hot swap in multiple ways, right? Okay, so where were we? Basically, max divided by min slowdown is a metric that is trying to balance the slowdowns. But one argument against it is, I don't care, right? What is the min slowdown? If a thread is going to go fast, let it go fast. Let it not be slowed down. What I really care about is the maximum slowdown that I bound in the system, right? The thread that has been treated the worst. And this is actually really important. It's actually, people have looked at fairness from an economic perspective, etc. They design max min fairness like we have devised, but there are arguments for this sort of fairness. Economically, what you really care about is the people who do worst. And you really want to reduce and reduce and reduce and reduce that max bound to a reasonable level. So this is also, there are also other papers that look at it from a theoretical perspective. And this is what we settled on also, saying that maximum slowdown is what we really want to bound. Okay, ideally, you would like to be here based on what I've shown in this picture. And if you look at the performance and fairness of different scheduling policies, none of them is ideal or close to ideal. So this is Atlas, good for throughput, not good for fairness. This is PARBS, good for fairness, not as good for throughput. This is STFM, not good for anything or average anymore, because that's what innovation is, right? Old policies become not good for anything. This is FR-FCFS, terrible, as we have discussed. This is FCFS, first come, first serve. Again, not bad for fairness in this particular workloads, happens to be, but not terrible for throughput. So basically, the realization is that no previous memory scheduling algorithm provides both the best fairness and system throughput. And we want to get the best of both worlds. So to enable this, we would like to actually look at how we treat these metrics differently. If you look at the throughput biased approach, usually the prior policies or the best prior policies prioritize less memory intensive threads. If it's less memory intensive, the thread gets higher priority. This is good for throughput, terrible for fairness in the end. So thread C is start, assuming that this is a static policy especially. A fairness-biased approach can take turns accessing memory across these threads. If you do this, then the heavy thread with a lot of memory intensity doesn't starve, but the light thread doesn't get prioritized, so you get reduced throughput. So the realization is that single policy for all threads is actually insufficient. You really want multiple policies to cater for these different things. I think of these as like smaller threads as mice, small mice. They can go quickly if you actually allow them to do. But these large threads are elephants. And if you actually are fair between mice and elephants, elephants will destroy the mice, right? So you need to be careful how you treat these threads. So how do you achieve the best of both worlds? This is a heterogeneous scheduling policy. For throughput, we're going to prioritize the memory non-intensive threads, these mice. These mice don't hurt the elephants unless there are so many mice, right? Which hopefully is not the case. We're going to limit that actually, as you will see. For fairness, the big fairness issues happen, so for throughput, we actually classify these threads that are non-intensive and prioritize them. That eliminates the mice out of the picture. Now, a lot of the fairness issues happen, assuming you eliminated these and treat them nicely for throughput. A lot of the fairness issues happen because these threads can hurt each other. Right? So different types of elephants. Think about some of the elephants are small, some of the elephants are big. And if one of them gets prioritized over the other one consistently, you're very unfair. So what we do is we're going to shuffle the thread ranking at short intervals. That way, every thread gets its share, if you will. But we're going to do it in a way that's aware of the characteristics of the threads. So we're going to shuffle asymmetrically. So that's the idea, basically. It's, again, a framework. We're grouping threads into different groups, as you will see. So we're going to group threads into two clusters based on their characteristics. Some of them are memory non-intensive. Some of them are memory intensive. We're going to prioritize the non-intensive cluster, which is good for fairness as well as throughput, actually. And then within each cluster, we're going to employ different policies. Inside the non-intensive cluster, we're going to prioritize for throughput because these threads do not hurt each other as much. They're not very intensive. Higher threads that are less intensive will get higher priority. Inside the intensive cluster, we're going to shuffle the thread ranking. So clustering, how does that happen? Basically, we're going to sort threads based on how much bandwidth they need from memory. And one way of measuring that is really memory misses per kilo instruction in the last level cache. And we're going to sort them based on lower to higher MPKI. That will give us a total memory bandwidth usage. You can sum up the MPKIs, for example. And we're going to allocate a small fraction of the memory bandwidth usage, say 10%, to an unintensive cluster. Threads that account for about 10% of the memory bandwidth usage will be assigned the memory non-intensive cluster, and they're going to be prioritized over others. Now, this is a threshold, which is not that great in the end, but it turns out it's not that bad also. A lot of these thresholding mechanisms are not perfect in the end, right? You may misclassify something. Okay, so this is what we do. And the rest is the intensive cluster. Between clusters, we're going to prioritize non-intensive cluster because non-intensive threads have greater potential for making progress. It increases system throughput. And this doesn't degrade fairness. That's the important realization. You prioritize these mice, but they're mice in the end. They're small. They don't hurt. They rarely interfere with intensive threads. And we've seen this before. This is not new. So within the non-intensive cluster, we're going to prioritize threads according to MPKI. I've already said this, but least intensive thread has the greatest potential for making progress in the processor. So we're going to have a ranking that looks like this, lowest to highest. Now, the interesting thing happens in the intensive cluster, where a lot of design decisions can hurt other threads. So the idea, as I said, is to periodically shuffle the priority of threads. So in shorter gain, finer gain intervals, you shuffle the ranking, such that each thread becomes a top thread at some point, right? So no thread gets prioritized consistently over others. That's the idea. This increases fairness by itself. The question is, is treating all threads equally good enough? Yes. Yeah. Mm-hmm. So it's not done arbitrarily. You could do random. The paper evaluates that actually. You could do arbitrary shuffling, which is not bad actually. But if you're actually more aware of the thread's request patterns, and not just the MPKI, but also the type of request, like streaming versus random, then you actually can do much better. Yeah, but that's a very good question, basically. You could do arbitrarily. Even in the PARBS paper, we looked at random ranking, for example, arbitrary ranking. Okay. Do random, yes. Exactly, yes. But it's yeah, exactly. It's not optimal. So basically, equal turns is not the same slowdown for different threads, and we have known this basically. If you look at a random access thread versus a streaming thread, and if you run them together, if you prioritize the random access thread, that slow down the streaming much less than if you prioritize a streaming thread. And you kind of expect that, right? We've seen this before, right? Streaming thread, if you prioritize the streaming thread, it hogs the row buffer, right? Whereas random access thread spreads its requests across banks. And if you prioritize it, streaming thread doesn't get affected as much. I'm going to show this again. So it's not old. This is relatively old news for you, but random access thread essentially looks like this. Whereas a streaming, basically it has high bank level parallelism. All requests are hopefully parallel. Streaming thread on the other end looks like this. It has high row buffer locality. And as a result, if you prioritize it over the random access thread gets slowed down a lot. So this is what happens if they're scheduled at the same time and if you prioritize a streaming thread. And we've seen this before, right? But this is another picture. We were looking at a single bank in the earlier picture. We're looking at multiple banks. Now you see the impact of the streaming thread on the random access thread even worse, right? So essentially, one request of a random access thread can get stuck behind a streaming thread. And this can be much worse if you have many threads, of course. So basically, we define a metric to identify the vulnerability of threads to interference. We call it the niceness. Niceness takes into account bank level parallelism as well as row buffer locality. And it turns out high bank level parallelism is usually a trait that is associated with vulnerability to interference, whereas high row buffer locality is a trait that's associated with, let's say, aggressiveness in terms of a threat. It causes interference. And the paper discusses basically multiple things over here. Ataberk is telling me that maybe I'm running late. Maybe not yet. So remind me 10 minutes later. Thank you. The paper discusses how to compute this niceness, and it basically computes a ranking based on this nice. I'm not going to go into the details of it, but I think this is actually a very interesting way of thinking about threads, right? It's really classifying the threads in a much more finer grained way. If you think about parallelism or batch scheduling, we looked at stall time, but we didn't really look at the look at things this way, right? Who is more likely to cause interference? Who's more likely to actually be vulnerable to interference? Okay, so the operation of TCM is also quantum based. Basically, we divide time into time quantums, and during a quantum, we monitor the thread behavior, memory intensity, bank level parallelism, row buffer locality. And at the beginning of the next quantum, we perform clustering and compute the niceness. And within a quantum, we basically shuffle thread rankings. So you can see that the shuffling is happening at a very fine granularity. Because time quantum is very long, if you actually do the shuffling across very long time quantums, then you actually can deny service for a very long time. We divide the time to smaller intervals where thread shuffling changes, and as a result, you get actually much better fairness across these intervals. Okay, there are a lot of interesting things over here that I'm kind of not going into a lot of detail, but we need to cover a lot of other things as well. So this is the scheduling algorithm in the end. It's a prioritization order again. Highest ranked threads, higher ranked threads are prioritized over others. This means that you have a priority bit for non-intensive cluster over the intensive cluster. Within the non-intensive cluster, lower intensity means higher rank, another set of priority bits. Within the intensive cluster, there's a rank shuffling based on the thread's characteristics. So you can think of that priority values are actually wider right now, right? And you compare these priority values. Assuming all else is equal, row buffer hits are prioritized over others, and assuming all else is equal, all disk requests are required over others. And it turns out this is actually also quite simple, as you will see in the paper. So we'll compare it to all of the prior works that we have discussed. Let's see where we end up. This is where different mechanisms end up. I think this is the same picture that we have seen earlier, maybe shown in a different way. Ideally, we would like to be better than PARBS and Atlas, right? And it turns out on these workloads, we were able to be better. You can see that this is better fairness as well as better performance than the previous best mechanism in either metric. So it's always good to achieve. And the way we achieve it is, again, with heterogeneous scheduling. So in a sense, this is kind of similar to heterogeneous latency memory, right? We have discussed earlier. We wanted to achieve both high capacity and low latency at the same time. And we kind of achieved that over there with heterogeneity, right? Different forms of heterogeneity. We've seen tiered latency DRAM. We also seen Lisa, where you actually can do caching. So there's heterogeneity across subarrays, for example. Here we again have heterogeneity. You want to optimize for multiple metrics, it's very hard to get away from heterogeneity. And heterogeneity always increases complexity. So there's another interesting thing over here that the paper also discusses. If you change the configuration parameter, for example, FR-FCFS at a cap parameter. In the STFM paper, we also introduced a policy called FR-FCFS cap, which is implemented in some AMD processors. Essentially, this tells you how many requests can be reordered over the oldest request that you have to exploit row buffer locality. That's the cap. And if you vary that, it kind of looks like this. Yes? Mm-hmm. Mm-hmm. Yeah. Yeah, so that's a very good question. Basically, a lot of the things that we have discussed actually are used also in the operating system literature, etc. But here, the scheduling is done at a much finer granularity at the nanosecond levels, as opposed to OS at the millisecond levels. So in all of these works, we don't consider the OS because the assumption is that OS has scheduled some threads, and internally we're trying to maximize the performance of that scheduling. But that's a very good question, basically. So in this particular case, the OS can actually change the configuration parameter to, for example, in STFM, it can change the unfairness threshold, right? Maximum tolerable unfairness. And it turns out these are not easy to reason about. PARBS, you can also change the batch size, for example. Atlas, you can change the quantum interval. TCM, you can change the cluster threshold. And at least for reasonable cluster threshold values, you get a fairness performance trade-off. All of those are period optimal. in this case, right, on that Pareto optimal curve. Okay, so you can have a relatively robust fairness throughput trade-off. So basically, there's more operating system support. I actually did not discuss operating system support in any of the prior works as well, but I'd recommend that you take a look at it. In the end, we want the memory controller policies to be programmable by the operating system, because as we discussed earlier, the operating system knows the goal, hopefully. It knows what it's trying to achieve. In this case, if it wants to achieve more fairness and less throughput, it can actually change the cluster threshold. It can also enforce thread weights. It can assign weights to different threads. And the thread cluster memory scheduler enforces weights within each cluster. This was true for the previous memory schedulers. We just didn't talk about that. Essentially, you want mechanisms to enable the operating system to say, I want to prioritize this thread because it's more important. In existing systems, this doesn't happen. At least it doesn't happen at the memory controller level in general, except for some cases where you may actually have, for example, a GPU, and you can specify a frame rate, and the memory controller treats that GPU specially. But within general purpose cores, usually the priority of different applications don't get communicated to the memory controller. And I think that's a huge shortcoming of existing systems. We will talk about scheduling. Maybe Ataberk will talk about scheduling across GPUs, CPUs, and accelerators, maybe briefly. But it's interesting that GPUs and accelerators are treated specially if you have an SoC, system on a chip. You can somehow enforce priorities of those accelerators and GPUs, but you don't have a lot of control over the priorities of CPUs. Those priorities don't get communicated, or general purpose cores don't get communicated to the memory controller. So our goal in all of these works is actually enable a much better communication across the system, from the operating system to the memory controller. Okay, so this is the conclusion. I'm not going to go through this is a summary of what we have discussed essentially. Let's talk about upsides and downsides. So at least on these workloads that we examined, we can provide both high fairness and high performance. I think the other interesting thing with TCM is it caters to the needs for different types of threads. So latency versus bandwidth sensitive at a high level, right? And even the operating system can do this assignment, right? We do the assignment dynamically, but the operating system or somebody who has a lot of knowledge about the applications, they can say, oh, I want the memory controller to treat these threads differently, right? So it could actually use the substrate. It's relatively simple, not as simple as Atlas, not as bad as STFM, relatively simple. But we're going to push for more simplicity in the later works, as you will see. As any idea, this also has downsides. We have actually shown that scalability to large buffer size is not that good. And we have some papers discussing that problem. Maybe Ataberk will cover. It's brittle in the sense that you have these clustering and shuffling algorithms, and they're all based on heuristics. And this is my criticism in general, as we discussed in the last lecture, right, of a lot of controller design and architecture and hardware and systems. A lot of heuristics everywhere, a lot of thresholds everywhere. Somebody needs to figure out what are good thresholds, good heuristics. And in the end, things become brittle. If somehow a thread goes into the non-intensive cluster, whereas it's somewhat intensive, it will hurt performance. It will hurt fairness also. So it's very important, I think, to come up with a way of robust way of determining these thresholds, heuristics, ideally seamlessly, right? A single threshold, regardless of wherever you draw that threshold, is a hard thing to really have, right? And I think that's a general criticism, but TCM also has its share because it treats the clusters widely differently, right? If you happen to mistakenly get characterized as a non-intensive thread, you get prioritized. If you happen to mistakenly get characterized as an intensive thread, you may be actually subject to all of these elephants stomping on you, right? So there's a brittleness. Ranking is still too complex, and we're going to solve that problem in a little bit. This is the paper. This is the top picks version. So I still like these ideas. I think a lot of these ideas have a lot of creativity. Any questions? Yes.
Software threads
and hardware threads. Is the buffer in the memory controller size of hardware threads? Yeah. So the memory, that's a very good question. In all of these works, we keep track of hardware threads. At some point, software may schedule another thread, but over time, the hardware will adapt because software scheduling happens at a millisecond level, right? if you're lucky, microsecond level. But we're really adapting to things at nanosecond levels. Right? So, exactly. Yeah. Exactly. We don't keep context information. But if your scheduling happens to be actually very quick at the software level, you may want to actually keep the context information, but we haven't gone to that yet in any of these works. Okay, if there are no other questions, now you're going to experience the concept of a hot swap. This usually happens, or context switch, meaning you'll selector. Oh, okay, you can take a break actually. How much break do you want? 10 minutes? 9 minutes, okay. So until 2:30 or 3:30. So it's not exactly a hot swap then. A hot swap happens when the processor is running and another processor kicks in and takes the workload off. All right. Yeah, thanks. See you guys.
No.
All right. I think we should get started because it's past 30 and we have like 100 slides to cover. I don't know what's going to happen. Just one quick disclaimer before I start. This is the work of Professor Mutlu and a bunch of other Safari members that were here, well, not here, but in Safari between 2007 and 2015, I guess. So I don't have the, let's say, as deep insights as Professor Mutlu has into these things, but I'll try my best to convey them to you. So we will continue with the blacklisting memory scheduler, which is another technique to improve fairness. And the key idea is simple, but let's start with the problem of existing techniques or the techniques we have described so far. The basic idea of fairness guaranteeing or fairness improving scheduling techniques is that they monitor the requests that come to the memory controller, and they rank the requests based on some scheduling policy. Now, to enforce the ranks, what Bliss claims or argues is that you will have a very complicated circuitry implemented in the memory controller because you have a lot of metadata that you need to check and decide based on in, let's say, one or few clock cycles. And that's what I was trying to convey. Basically, full ranking, ranking these requests increases the critical path latency and area. But you do this in order to improve fairness and performance. Now, Bliss is kind of adding another dimension into this trade-off space of like fairness performance. And now we have simplicity. Simplicity in terms of mostly hardware complexity that can be area and latency overheads of the hardware that you need to implement. So this is our radar chart, where the ideal is basically trying to show you where we want to land on in this trade-off space as Bliss. And here's how FR-FCFS looks like. Basically, we'll place existing scheduling techniques into this radar chart. So I'm going to skip this, or I'll go relatively quickly, but you can interrupt me to ask questions. And the idea is that, of course, Bliss is going to aim to, get as close to ideal as possible. So the key question they ask is it essential to give up simplicity to optimize for performance or fairness? The answer will be no, and Bliss will land on the radar chart as such. So the observation is it's enough or sufficient to separate applications into two groups rather than, a bunch of more groups, or rather than doing full ranking. You don't really need to rank all of these requests based on a policy. So this is a small example that's showing you only 4 requests, right? But you can have, I don't know, up to 30, 60 requests in your memory controller request buffers. So this gets complicated as you add more requests. No, you don't want to do this. And instead, you have 2 groups that you're categorizing your requests into. That's the interference vulnerable group and the interference causing group. And this will be enough to achieve fairness and improve performance. And then the idea is you will prioritize the interference vulnerable requests over interference causing requests. This is much less complicated in terms of latency and area, and we will have some results that show that compared to full ranking, and also has lower slowdowns than ranking. Now, how do you classify these applications into groups? Basically, if you serve a lot of applications from the same, if you serve a lot of requests from the same application, you will cause interference. These requests will interfere with requests from other applications. And you consider these applications with a large of requests as interference causing. And you blacklist them. What does that mean? So you basically keep a record of these applications that inject a lot of memory requests to your to the memory controller queues, and you will deprioritize them. And as long as they're in this blacklist, you're not giving them priority over other applications, but you will periodically clear this list. And this enables lower complexity. And it allows you to do finer grain grouping decisions, and leads to lower unfairness. And that's how you land closer to the ideal in the radar chart. Now, the finer grain results they will look like this. So you have unfairness on the y-axis, performance on the x-axis, and ideal is in the right bottom right corner. So here's how the existing scheduling techniques look like when you place them in the chart. I think we've seen this in TCM also. Bliss performs 5%, achieves 5% higher performance than the best performing scheduler, while also reducing unfairness by 21%. So it achieves higher performance, and it kind of balances performance and fairness. As for complexity, this is where the real benefits, I guess, are coming from. I would say are coming from. So you put Bliss over there compared to TCM, it's 43%. It takes 43% less area to implement in the memory controller. And it has a critical path latency that's 70% smaller. So arguably, Bliss is, much easier to implement in a memory controller and integrate it into the memory controller pipeline. It reduces complexity significantly. That's basically the summary of Bliss, and you can find more information about blacklisting memory scheduler in this paper, and there's a longer paper. If you're interested, please check them out. So we'll now kind of switch gears into a different interference problem. We're going to look at multi-threaded applications. We've been ignoring them for a while now. There's, of course, some basically full-length lectures on these. I will only have like 10 slides to cover. multi-threaded application scheduling. But Professor Mutlu has more lectures on these topics. So if you're in the end, if you're interested, go check them out. But I'll try to give you the key problems and ideas. So threads in a multi-threaded application can be interdependent as opposed to threads from different applications. What does this mean? If you slow down one thread, the other threads may slow down or may speed up, right? This is the same application though. These threads need to synchronize with each other. For those, we use locks, barriers. Does anyone not know what locks, barriers, or synchronization primitives are? Okay, that's good. And then some threads will be on the critical path, and some threads won't be. And this will become more clear in the next slides. Yeah, this is basically just elaborating on the problem. Okay, yeah, I mean, critical sections, they enforce mutually exclusive access to shared data. What does this mean? You have a code. Each thread of an application is executing this loop where you compute for some time. This is like the normal region of your code. And then there's a critical section whereby you lock you acquire a lock, and then you do some operation and on shared data, and then you release the lock so some other thread can lock it and do the same operation again. Only one thread can be executing this at a time. And then if you look at a diagram of basically two threads executing this loop, you'll see that one thread will take slightly longer to execute the normal region or normal code or regular region, whatever, because of some, I don't know, basic undeterministic latencies maybe in the memory hierarchy, right? One request took 45 nanoseconds more to execute than T2's request. And then that means T2, in this case, will acquire the lock earlier than T1. And then T1, once it's done executing this normal region, it will have to wait to acquire the lock for a while. And this is the time that T1 spends idle. Now, I guess you could fill this time up by scheduling other threads from an OS perspective, but we are looking at this as if this is the only application we're running in the system, right, to simplify things. And then this will cause the, this contended critical section will cause T1 in this case to wait, as I just described. Also, there are barriers. These are synchronization points. Another example to like using barriers as a synchronization points, where you have each thread executing two loops. They do some compute, and every thread will basically do the computation on loop one, and then they will wait for each other to complete to get to that point. And this is how that looks like, right? In this case, T2 reaches the barrier much later than T1. And then you're spending some time doing nothing for T1, in this case, until T2 reaches the barrier. And then they have to wait, and this is what I just said. You also have the concept of stages in pipeline programs. So basically, you have multiple barriers between different compute regions in your code. We will call them A, B, and C. So each thread is executing this loop again. And this is how it would look like if you were to draw a pipeline diagram of the stages of your code. And this is just showing you what each thread is executing. And then you have a picture like this. Again, you're seeing the idle time. Basically, the thread that executes the slowest stage is on the critical path, and that causes some idle time in the other threads. In this case, B is the slowest one, and then A and C are struggling. Well, they're not doing anything useful rather than struggling. The key idea is basically if you could reduce this time spent, you could improve performance or utilization at the very least, right? You're making better use of your cores. Now, how can you do that? Well, the key idea, the only key idea we'll describe will be if you can estimate these threads that limit performance. In the previous case, it was B, and you prioritize it over other threads in your whole computer system. But we will apply the idea to we can choose to apply the idea only to memory controllers. Right? Once we identify the limiter thread and we want to prioritize it, we can choose to prioritize its memory requests in the memory controller. And that will reduce the time B takes to get to the barrier. And by doing that, we have reduced the essentially overall time other threads spend idle. And then for non-limiter threads, those are A and C in the previous picture, you can just shuffle priorities to reduce interference among them. How do you estimate limited threads? Well, there are, I guess, 3 ideas how you can do that. If you can find the most contended critical section in a program, in a multi-threaded program, you can choose, or you can determine the thread at a time executing that most contended critical section to be the limiter thread. You can again determine the thread that executes to slowest pipeline stage as the limiter thread, or that's falling most behind, assuming you can identify these conditions. Now, how would that look like? So this is another diagram that shows you what each thread is executing at a time. We have critical sections. Those are the green and orange rectangles here. Sorry, the green one is a, okay, wait. Yeah, those are the critical sections. And the blue dashed lines show you the amount of time each thread is waiting to sync or acquire a lock, synchronize or acquire a lock. Now, this is one way to identify a critical path, I would say. So how would you do that? Well, you don't have this information. You're trying to profile the application as it's running. So you're running this workload, and you're at a time t. That's basically where my pointer is. The most contended critical section up until now is critical section 1. That's the green rectangle. Now you execute the programs a little bit more. You know which thread is on this most contended critical section. That's at this point in time, that's thread D. So the idea is you're prioritizing thread D's requests over other threads so that it makes faster progress. And by doing this at each step, by identifying the thread that's running the most contended critical section and prioritizing it, you can reduce the execution time slightly such that they reach the barrier earlier than when you don't prioritize any of them. Now, I won't go into the details of how you can do this exactly, but maybe I'll show you this analysis of upsides and downsides of PAMS or parallel application memory scheduling, the paper that I guess that describes this idea. It improves the performance of multi-threaded applications, and it provides a mechanism to estimate limiter threads. And then it opens a path for slowdown estimation, because it showed that if you could estimate slowdowns for multi-threaded applications, you can improve the performance of multi-threaded applications, essentially. And there were some follow-up papers that I will flash in the next few slides. The downside is if there are multiple multi-threaded applications running together, what do you do? Well, I don't know. Think about it, I guess. And the thread estimation, although I didn't go into the details, can be complex. So these are things you could think about, I guess, maybe as you review this lecture, if you do that. And then there's this paper that's like a follow-up work to this one that, if I remember correctly, shows describes an easier way of coming up with a limited thread estimation methodology. That's PAMS, if you're interested in this paper. And of course, I'll refer you to this lecture on parallel application scheduling if you like the idea of improving performance for multi-threaded applications by prioritizing one over the others. And then this is the other paper that I told you about that provides a different methodology for limited thread estimation. And finally, this is yet another methodology to identify the limiter thread, but also in a different system configuration. You have a heterogeneous or asymmetric compute units where you have like more powerful cores and less powerful cores in the same system, and you're trying to figure out which thread to place where. If you put a thread in a powerful processor that will execute faster, that's a way of prioritizing the thread. Okay, that's it for multi-threaded workloads, actually. And we'll move on to heterogeneous systems. How am I on time? 15 more minutes, good. 100 more slides to go. Memory scheduling, so okay. We're gonna look at heterogeneous systems, and if I remember correctly, I'm not gonna go into details of any scheduling technique here, but this is what we have in today's systems. We have an SoC that has an asymmetric, compute cluster. Basically, you have large CPUs, small CPUs, some caches, GPUs, hardware accelerators, and other engines that all share main memory, or well, if you're future-looking hybrid memories. And the question is, how do we allocate resources to these agents in a way that we mitigate interference and provide predictable performance? We'll look at interference, or I will just flash you some papers that look at interference problem, and then we will go to predictable performance next. So again, another system that has a lot of well, agents and shared resources, right? And of course, Professor Mutlu has lectures that are dedicated to these. So if you're interested in what I'm going to talk about, you can refer to these slides. These videos. Now, one work that deals with this problem is stage memory scheduling. The problem is basically when you have a GPU sharing the memory controller with CPUs. We've looked at the memory controller in context of basically only CPUs accessing the sort of main memory, right? Because we were thinking about requests. Well, a relatively smaller number of requests arriving at a time to the memory controller. Now, when you have the GPU wants to make very high throughput access to main memory. That means you will have a bunch of requests getting injected to sort of memory controller request queues, maybe hundreds. And then if you have hundreds of requests in the controller request queue, you cannot just design a memory controller that is, let's say, relatively low complexity, that has a relatively low complexity and is able to look at all the requests and try to pick which one to schedule, because it needs to go through hundreds of requests to find out what's next to schedule. And SMS, or stage memory scheduling, its key idea is to basically divide the memory controller's responsibilities into respective pipeline stages, let's say. And you still have a large buffer that can accommodate all the requests coming from the memory, the GPU and the CPU, but you're not trying to pick the best request to schedule from that large buffer. Instead, your only goal in the memory controller pipeline stage that looks at the buffer is to find out the requests that go to the same row, and you batch them. And the rest of the memory controller now just tries to schedule the best batch instead of the best individual request. And with that, you can achieve a relatively practical memory controller design that has a very large buffer. And why do you need a very large buffer? Because basically you have these heterogeneous agents that are popping up. Well, back then it was, I guess, 2012. Now we have GPUs everywhere almost. But when you think about the SoCs from 2012, I guess the GPUs were being added to the same die as the CPU just lately, right, back then. And then you need the large request queue because the GPU will have spatial locality in its accesses. You want to be able to collect all these requests that go into the same row. That's the main reason why we want to have the very large buffer. Okay. Now Dash is again looking at heterogeneous architectures where we have multiple agents, but here the goal is to have hardware accelerators that have specific deadlines for their, maybe let's say the computation deadlines, right? You give it some task to the hardware accelerator, decrypt this key or whatever. Well, decrypt this message using the key or whatever, right? But that has to end at time t. That's the sort of the background and the task we have at hand. Now, the state-of-the-art memory controllers then were prioritizing this hardware accelerators requests only when you were very close to the deadline. Right? Its priority increases as you get closer to the deadline. And when that happens, the hardware accelerators still have a lot of requests in the buffer waiting. And when you prioritize that hardware accelerator at that point, you have to schedule a lot of requests before you can schedule any other requests from any other application. And that slows down your applications significantly. You don't want that, and Dash is, basically this is the problem Dash is dealing with, and I won't go into any further detail. If you like the problem, read Dash, and I hope you will be satisfied. And finally, there's decoupled direct memory access. Here we're looking at, again, the same heterogeneous system, multiple agents trying to use main memory. The idea is to have a dual port DRAM or main memory, whereby one port is allocated only for I/O stuff like DMA, for example, direct memory access, retrieving data from from hard disk and putting it in the main memory. Normally it would go through the processor, or at least the DMA, but through the same channel that all other application requests also go through. Now, by decoupling the CPU interface from I/O interface, you're essentially basically not having a situation where I/O requests can interfere with CPU requests. Now, this has a cost, and the paper evaluates that, and it has significant performance and energy benefits for systems like this. Okay, 8 more minutes, good. Now we'll go to service guarantees. This is quality of, this is going to be about quality of service. So now we're dealing with the predictable performance aspect of allocating resources in heterogeneous systems. Again, there are lectures that are dedicated to this, and these are the links to them. This paper we will describe in detail, I guess in another lecture now that I have 7 minutes left. These are the papers that deal with this problem, basically. I'm going to flash them to you. Some of them I already showed you, some of them I already showed. Okay, maybe this went too fast. Interesting. Yeah, anyways, we will go back to this problem again. So we will look at other QoS approaches instead. I think we talked about prioritization and request scheduling up until now, and now we're going to look at only a few works from each of these remaining techniques. That's data mapping, core or source throttling. Instead of throttling the requests, we are going to throttle the request generators, and then application scheduling. Dedicated lectures are available for this component of this class as well. And okay, we will talk about memory channel partitioning, and I think that's where we will have to end the lecture. But yeah, so the idea here, or maybe the system we have today, we have multiple cores, we have multiple memory controllers attached to different memory channels. And these channels are obviously like independent from each other, right? How do we map data though? We have the red application running on one core, we have the blue application running on another core. We're gonna distribute the data, or we're gonna allocate data to these applications in a way that we don't consider basically the channels being independent. This is what we do before this idea. And you can already see that blue app will interfere with red app's requests, right? Because they're sharing channels. Now, instead, you could just allocate one channel to each application. That's the basic idea that this paper proposes. Of course, it's going to be more detailed than that. And we're going to go into a bit of the details. But this way, you can already see that you eliminate the interference between red and blue apps application requests. So the goal is to eliminate interference. And the basic idea is to map data to different channels for different applications. But there are two key principles or data mapping principles that MCP or memory channel partitioning applies. That is to separate low and high memory intensity applications from each other and low and high row buffer locality applications. Why? Because high memory intensity applications interfere with low memory intensity applications, as you saw in TCM, right? So this is going to be a pictorial depiction of that again. You have the red app that is going to be high memory intensity. So this is basically showing you at what time its requests are scheduled to which channel and which bank. So we have a bunch of red application requests. And we have only a few blue application requests. And if you don't prioritize blue application over red, you will see that with the conventional page mapping, it takes us 5 time units, arbitrary units, to schedule all these requests. If you could allocate one channel to each application, that brings the amount of time units down to 4. And this allows you, at least for the blue app, to save a significant number of cycles or time units. And for the red app, you still have some savings as well. And that is the first principle. The second principle is, or the reason why we have the second principle is because high row buffer locality applications interfere with low row buffer locality applications. Those are random access applications. You can think of them as that. So you have these, okay, in the conventional mapping, you have a low row buffer locality application that's R1, that's the blue app. You can see which rows its requests go to. That's R1, 2, 3, and 4. And then there is the high row buffer locality application, the red one, which accesses row 0, but its accesses take a smaller time because it has row buffer locality. So if you could partition the channels again to each application, you save a lot of time units, right? And the mechanism looks kind of similar to what we have seen. I think, again, I will give you the example of TCM. You profile applications, and then you classify them into groups, partition the channels. Now, the key, I guess, downside here is, I'm going to skip a bit fast. Okay, it provides benefits over existing scheduling techniques. Maybe this example is, this is where Onur is right now. He's going to the airport. And this is what he would like. He likes to give as an example for bad channel partitioning, where you have 2 escalators not utilized and just everyone on one escalator. But the reason for that might be something else, right? Maybe the escalators are going up. Still, fundamentally, you could rotate them and then allow more people to use them. Anyways, I was going to talk about the key downside. The upsides hopefully are somehow clear. I don't have much time, but you have to move pages between channels when you want to apply this. So basically, you profile the application in one time quantum, and in the next time quantum, if the decision is to isolate the pages of that application from another application, you might have to move all the data to the other channel, and that induces a lot of overhead. So that's good to think about, and how to reduce it. Maybe it's a good idea. I have to, I guess, stop. So thank you. I guess if you have any questions, I can take them now. Otherwise, what? I can do that. It's fine by me, but I don't know the plan.
Yes.
Yeah. Okay. Probably. Yeah.
Memory bandwidth to the host.
Mm-hmm.
When you partition and put coordinates from one side and high
Mm-hmm. This is correct, but at the same time, if you were to not partition them, you're increasing the unfairness for one application, right? Yeah, so it's like a trade-off. You have it here as well. Yeah, the fundamental trade-off doesn't change, really. So speculatively, I'll say that we will continue tomorrow with these, but that's not for sure. Maybe in a later lecture, Onur will come back and describe the remaining stuff. Okay, thank you, everyone. See you next time.